Alright, hello everybody. This is Dr. Pennington again, and in this video I'd like to talk to you about the concept of something called Henry's Law. Now this is something that you will have all seen before in one form or another, and probably the simplest explanation of what's happening here is think about a bottle of soda. And here's my fabulous representation of a bottle of soda. There's the top. Let's say it's some Coke with that lovely Coke logo. Alright. What happens when you take off that cap? Well, of course, what you hear is a fizz. Now, what's actually happening that accounts for that fizz? Well, something's being released. And of course, that gas that's being released is CO2. And so the question is, well, where's the CO2 coming from? Well, the CO2 was originally dissolved inside the solution. Alright. Now what Henry's law states is the solubility of a gas within a solution is proportional to the partial pressure of the gas above that solution. So the point is, in that bottle of Coke you have a lot of CO2 dissolved in there, and the pressure up here in that little space up above the solution is very high. Alright. So the partial pressure of that CO2 there is very high. If I then open that top, the partial pressure of CO2 goes way down because it gets exposed to the atmosphere. So the partial pressure of CO2 goes way down when it gets when the bottle is opened, which means the solubility of the carbon dioxide within the solution below it also goes down. That's why when you pop the cap, the bubbles come out, because as you make the partial pressure of CO2 above the solution lower, the solubility goes down as well, and because the solubility goes down, the CO2 comes out, and so that's what you see as bubbles. So the actual equation for what Henry's law looks like is really very simple. The solubility of any gas, we'll just say S for solubility here, is equal to the Henry's law constant, unique for every gas, times the partial pressure of that gas, whatever gas we happen to be talking about. Now, like I said, the Henry's law constant for every gas is different, and this is temperature dependent too. So for now we're just going to assume things are done at 25 degrees C. So the Henry's law constant for oxygen, this is not something you need to know, it's just something you're going to need to know how to use. At 25 degrees C is 1.3 times 10 to the negative 3 molarity per atmospheres. Now the other way of saying that is moles per liter atmospheres. So make sure you understand that this and this are the same. Alright, two different ways of writing out the same units. Personally, I prefer to use this because then I get rid of any ambiguity about my big M and where the moles and liters go, so these are the units that I'm going to stick with. So we have that. Let me just write that out again. The Henry's law constant for oxygen, 25 degrees C, is 1.3 times 10 to the minus 3 moles per liter per atmosphere. So let's say we had a situation where we had a bottle of something with some dissolved oxygen in it. And what if we wanted to find out what the concentration of that gas was within the solution? So let's say we had a container that had some water in it, that had some O2 dissolved in it. We can figure out that solubility, and really all solubility is just a concentration. So the units for that are moles per liter. So that's what you'll see solubility units as. This concentration or solubility, or whatever you want to call it, is directly proportional to the partial pressure of the CO2 above that solution. So let's say the partial pressure of CO2 above that solution of oxygen in water is, let's see, what should we say? Let's say 0.03 atmospheres. Okay, Actually, you know what? That's kind of low. Let's make that higher. Forget that. Let's make it pretty high. Let's make it 3.72 atm. 3.72 atm is much higher pressure than what we would experience normally. What we experience is about 1 atmosphere. So we can figure out the solubility or the concentration of that CO2 of that oxygen dissolved in that gas just by using this formula. You remember I said the solubility was expressed in units of moles per liter? Well, we're going to see that these two guys, the units will cancel out to give this. We know already that the Henry's law constant for oxygen is this, because that's what we were told before. And we know the partial pressure of the oxygen above. Sorry, that should be... Sorry, I'm making mistakes all over the place here. Sorry guys, I just noticed that should be partial pressure of oxygen, not CO2. I have CO2 on the brain. There we go. So the partial pressure of my oxygen here is 3.72 atmospheres. Of course, I didn't prepare this morning. I haven't got my calculator to hand. So let me just find that. Alright, so 1.3 times 10 to the minus 3 times 3.72 gives us 4.836 times 10 to the minus 3 moles per liter. Remember I said before the concentration of solubility is always expressed in moles per liter. And if we had to do this to 3 significant figures because of this guy here, of course that would be 4.84 moles per liter. So that's the important thing about Henry's law, that it's used to correlate the relationship between the solubility or concentration of gas dissolved in a solution with the partial pressure of the gas above that solution. Alright, now let me go through a question here that's a little bit more complicated. It involves Henry's law, but there are other things too. Alright, let's see. Let's take a look at this question. It says, what is the amount in grams of nitrogen gas dissolved in an 80-liter tank of water? Assume that the mole fraction of nitrogen in the dissolved gas is 0.78 and the total pressure inside the tank is 1 atmosphere. Alright, so when we have a question like this, the most important thing is to figure out, well, what information do I have? What do I know? So let's write down what we know. We know that the volume of the tank is 80.0 liters. We know the pressure, and this is important here, total pressure. We know the total pressure inside the tank is 1 atmosphere. And we also know that the mole fraction with that funky symbol of nitrogen, remember that's N2, is 0.78. Now just to refresh you guys about what mole fraction means. Alright. If I have 2 different gases in a solution or in a mixture, and say they're in a 80-20 ratio, then one is going to exert 80% of the pressure, number of moles, and the other is going to exert 20%. So if the mole fraction of nitrogen in the gas is 0.78, then that means 78% of the gas is nitrogen. Doesn't matter what the other gases are, but 78% of that is nitrogen. And the thing that we can do here is we can take the total pressure inside the tank, use the mole fraction of nitrogen to figure out what the actual pressure inside the tank is coming from the nitrogen. So if you think about it, if the total pressure inside the tank is 1 atmosphere, alright, and if your mole fraction here is 1 in total, 0.78 of that is nitrogen. So therefore that means 78% of that pressure is coming from the nitrogen. So that means 1 times 0.78 will be the number of atmospheres corresponding to the pressure exerted by the nitrogen. And we can actually write a formula for that. The partial pressure of nitrogen is equal to the mole fraction of nitrogen times by the total pressure inside the tank. or the total pressure of gas in the tank, which in this case for us, just like we said, is 0.78 atmospheres. We have no units here, this is just a ratio, so therefore that's why the units here is atmospheres. So now we have the partial pressure of nitrogen, and we are ultimately looking for an amount of nitrogen in grams, and we've got to use this volume. So, well, let's think. We've been talking about Henry's law. What do we know? We know a partial pressure of nitrogen. If we go back here, we can see, oh, you know what? If I have the partial pressure of a gas, and I know its corresponding Henry's law constant, I can calculate the concentration of that gas. Well, that would help, because I need to get to grams. I can get there from a concentration. So therefore we can apply Henry's law and say, well, the solubility of nitrogen is going to be equal to the Henry's law constant for nitrogen, and we can look that up, times the partial pressure of nitrogen, which we just found. All right. Now it turns out that the Henry's law constant for nitrogen is 6.1 times 10 to the negative 4 moles per liters per atmosphere. Notice that these units are exactly the same as these units here. All right. The partial pressure of nitrogen we just calculated to be 0.78 atmospheres. So therefore the solubility, or the concentration of nitrogen within this solution, if we get rid of those two sets of atmosphere units, is 4.76 times 10 to the negative 4 moles per liter of nitrogen. Now, how can we get to grams here? Well, usually we get to grams from moles. So how can we use this to get to moles? We have moles per liter, and the answer here is, well, we have the number of moles per 1 liter. But we don't have 1 liter, we have 80 liters. So therefore, 4.76 times 10 to the minus 4 moles per liter of nitrogen. We're going to multiply all that by 80 liters to find out exactly how many moles we have. But then I want to go from moles to grams. Alright, so if I cancel out these, I have my answer in moles, but I don't want moles, I want grams. So I've got to remember, well, how many grams are in 1 mole of nitrogen? Well, 1 mole of N2 is 2 atoms of nitrogen, so that's 28.02 grams of nitrogen. Now let's just check. Moles, moles, and we end up with grams. And if we calculate all that out, what we end up with is 1.07 grams of nitrogen. What this means is, in that 80 liter tank, where the mole fraction of nitrogen is 0.78, the number of grams of nitrogen dissolved in that gas is 1.07. So that's a slightly more complicated question involving Henry's law, but we used it right there. And we went through the basics of what Henry's law is all about, and that is it. Thank you.